All right, lucky number 13 here on the math subject GRE practice test. This is actually my third time doing this problem, thanks to some lovely technical difficulties, but hopefully it'll record this time. This problem, kind of a fun one. We get into, I guess, some really elementary graph theory, although really it's more combinatorics that you do to solve this thing. And while I find the problem kind of fun, I don't think it's a great test problem. This is actually a really famous problem, sometimes referred to as the handshake problem. And using a famous problem like this just feels kind of lazy by the test makers. I mean, there's nothing wrong with the problem itself, but I imagine some of the people taking this test will have seen this problem before, and some will not have. Those who have would have a distinct advantage and likely be able to solve it a lot quicker, which just sort of feels unfair. But whatever. Guess that's life. So what's going on in this problem is we have this graph, which is really just a collection of edges and vertices. And we're told that for every two distinct vertices, there's an edge connecting them. And somewhat redundantly, every edge connects two distinct vertices. Okay? In case you have a hard time visualizing that, here is a graph with 5 vertices. And what this statement is saying is that every pair of them is connected with exactly one edge. So the graph looks something like this. This actually has a name. It's called the complete subgraph on 5 vertices. And by just kind of counting, we can verify that this has 10 edges. Unfortunately, 10 is a long way from 190, as we can see if you look at the different choices of the number of vertices that the answer has. So what do? Well, one strategy might be to start with simpler cases. Presumably, we'd just be able to count the edges for subgraphs with fewer vertices, and then maybe there's some sort of pattern that we can exploit to figure out how many vertices we'd need to get 190 edges. So let's see, if you just have one vertex, how many edges? Well, none of them, because you need 2 vertices to define an edge. If you have 2 vertices, you can connect those 2 vertices with an edge, and then you're done. So that subgraph would just have one edge. If you have 3 vertices, maybe you can picture in your head what your graph would look like and how many edges you'd have. If you're thinking 3, that's wonderful. Here's my 3 vertices. In order for every pair to be connected, my graph would look something like this, 3 edges. Pretty little triangle. And you're like, okay, I'm getting the hang of this. If we have 4 vertices, we'd have a square, I guess. So there'd be 4 edges, right? No. I mean, you'd start out with the square, but we haven't connected all the vertices, right? We haven't connected the diagonal pairs, so we'd have to add 2 more edges. Our graph would actually look like this. We'd have 6 edges. We've already seen up here that if we have 5 vertices, we got 10 edges. And well, you could keep drawing the different pictures. Maybe this is sufficient to figure out a pattern. Stare at these numbers for a little while, and you might recognize that when we go from 1 vertex to 2 vertices, the number of edges we have increases by 1. When we go from 2 vertices to 3 vertices, the number of edges increases by 2. From 3 to 4, the number of edges increases by 3. From 4 to 5, the number of edges increases by 4. It sure does look like we got the start of a pattern here. In fact, you can verify that pattern if you think about what would happen if we added a 6th vertex up here. So I don't know, maybe I'll throw it off to the side here. Well, we know that all these pairs are already connected, so the only additional edges we'd need are edges from this new vertex to each of the 5 vertices that already exist. Since there were 5 vertices before we added this 6th one, we'd need 5 new edges. In this 6 vertex case, we got 15 edges. Instead of thinking about this 6 vertex case as having 15 edges, we can think about it as having 1 plus 2 plus 3 plus 4 plus 5 edges. Similarly, the 7 vertex case we could think about as having 1 plus 2 plus 3 plus 4 plus 5 plus 6 edges. Or more generally, the n vertex case would have 1 plus 2 plus 3 plus all the way up to n minus 1 edges. So since this question tells us that we have 190 edges and asks us how many vertices we have, really all we have to do is solve the equation. When does 1 plus 2 plus 3 plus all the way up to n minus 1 equal 190? Our solution for n will be the number of vertices, which will be the answer to the question. How do you solve this equation? Well, again, there's options. The first option is have a formula memorized. Turns out that if you add all the positive integers from 1 all the way up to, I don't know, k maybe, you get k times k plus 1 divided by 2. If you have this formula memorized, then all you got to do is change all the k's into n minus 1s, and you get that the sum from 1 up to n minus 1 is equal to n minus 1 times n minus 1 plus 1 divided by 2. Well, since n minus 1 plus 1 is just n, I get n times n minus 1 over 2. I want to know what n is equal to when this thing equals 190. All I got to do is solve this equation. If I multiply both sides by 2, I get 380 is equal to n times n minus 1. If you're algebraically inclined, you might kind of autopilot distribute this n through. Recognize that you have a quadratic trinomial, factor and solve. And that's totally fine, you can do that. but you can also just stare at this thing for a little while and be like, wait a minute, I got some number and I'm multiplying it by one less than that number, and the product is equal to 380. Well, let's see, 20 times 20 is 400. 20 times 19 would be 380. Looks like n is equal to 20. If you have a hard time seeing that, fine. 380 equals n squared minus n. Subtract 380 from both sides. You got n squared minus n minus 380 equals 0. And solve this thing. How do you solve it? Up to you. Quadratic formula, complete the square or factor. If you factor, you're looking for two numbers that multiply to negative 380 and add to negative 1. Those two numbers are negative 20 and positive 19. Although if you're able to figure out the two numbers down here, you probably could have figured them out up here, as it's essentially the same problem. Anyways, n minus 20 equals 0, so n equals 20, or n plus 19 equals 0, so n equals negative 19. N is assumed to be a positive number, so we can ignore this solution and get n equals 20 as our answer. Go back up to your solutions. Looks like that's answer C. We've answered the problem. Cool. But if you take a look at the time left on this video, you see there's still a lot of time left because I still got a lot to say. First thing, if this algebra gives you any trouble, when you're at this stage right here, or maybe it's easier to use this line here, you easily could just take the different answers and plug them in and check. Which of these answers times one less than that answer is equal to 380? 18 times 17, is that 380? Nope. 19 times 18? Nope. 20 times 19? Yup. Done. When you're taking your test, don't forget it's a multiple choice test. Sometimes you can save yourself some work by only considering the answers that they give you as possibilities. Other thing, I got two arrows here. That implies there's another way to do this if you don't have this formula memorized. Turns out you can derive this formula pretty easily. The derivation is pretty famous. It's typically attributed to Carl Friedrich Gauss. Sometimes it's called Gauss's method, although Gauss was kind of a genius and had methods for everything, so maybe Gauss's method for addition of integers or something. I don't know. What's kind of fun about this is there's a story to it. The story is probably completely false, but every teacher I know always tells this story as though it's true. The way the story goes is a young Carl Friedrich Gauss was kind of dominating his elementary school, answering every math question the teacher asked before any of the other students had a chance to even consider it. So the teacher had the bright idea to give Gauss some busy work to try to kind of shut him up for a little while. So the way the story goes, the teacher asked Gauss to add up all the positive numbers, positive integers, I guess, from 1 up to 100. And the way the story goes is that Gauss thought about this for a second or two, and then immediately told the teacher that the sum would be 5,050. Teacher didn't believe him, went and checked, he was right. The rest is history. Well, the teacher assumed that Gauss was able to do 1 plus 2 is 3, plus 3 more is 6, plus 4 more is 10, plus 5 more is 15, all the way up to 100 kind of instantaneously. Supposedly what Gauss did is considered two copies of this sum. So maybe we call our answer, I don't know, x. Well, if x is 1 plus 2 plus 3 all the way up to 100, x is also 100 plus 99 plus 98 all the way down to 1, right? Addition is commutative. Rather than figure out each of these sums individually, we could add them vertically. 1 plus 100 gives us 101, 2 plus 99 gives us 101, 3 plus 98 gives us 101, and so on. If we add the right side of these two equations, we just get a whole bunch of 101s. If we add the left sides of these equations, we get 2x. How many 101s do we have over here? Well, we got 100 of them because the columns are kind of numbered 1 to 100. So we know that 2x is equal to whatever 100 times 101 is. You can either multiply by 100 and then divide by 2, or divide by 2 first to make this 50 times 101, because 50 times 101 is pretty easy to do. 50 hundreds is 5,000 and 50 ones is 50. So we get that this sum is equal to 5,050. In all likelihood, you're not going to be asked to sum the numbers from 1 to 100 on your test, but there's a decent chance that you can use this formula right here. And maybe you'll just memorize it, but maybe it'll be easier for you to memorize it if you think about, if I just took this sum and wrote it backwards, I'd have a whole bunch of, k plus 1s. How many of them would I have? I'd have k of them. So if I add up those k plus 1s, I'd get k times k plus 1. But be careful, that's not the sum, because in order to get those k plus 1s, I need 2 copies of the sum, so I have to divide by 2. What else do I have to say about this problem? Oh, I told you it was called the handshake problem. You're like, where do the handshakes come in? Well, we were able to figure out that if we have n vertices, the number of edges that we'd have would be the sum of the positive integers from 1 up to n minus 1. We kind of did that by considering some cases, discovering this pattern, which we actually kind of justified a little bit, and then coming up with this formula. However, you can come up with this formula without ever considering smaller cases, which is kind of cool. That's the idea with the handshake problem. For the handshake problem, suppose you have n people in a room. N can be whatever number you want. They're all just kind of mingling about awkwardly. It's really important to you that everybody meets everybody. And meet in this context means shakes hands. But being the mathematical nerd that you are, you want to make very careful that no two people meet each other twice and that everybody meets each other. So can we devise some sort of an algorithm for making sure that everyone shakes everyone's hand? Well, sure. One way you could do it is pick one person, one special person, this person right here maybe, and tell that person, walk around and shake everybody's hands. They're like, all right. We started out with N people, told one of them to shake everybody else's hand. That person just went and shook N minus 1 hands. I'm not going to draw the edges because that'll get all nasty, but think about shaking hands as creating an edge. We've had N minus 1 handshakes, but we're not done. Most people have not shook each other's hand. This person has shook everybody's hand, so we're done with this person. We tell this person, leave the party, get up out of here. This person's gone. Then we pick some other person, the second most special person in the room maybe, and we tell them, shake everybody's hand in the room. Note, they don't need to shake the hand of the purple person. They can't, that person's gone, but that's okay. These two people already shook hands when it was the purple person's turn. So how many hands is this red person going to shake? Well, we started out with N. They ain't going to shake their own hand, and they've already shook purple's hand, so they're going to shake N minus 2 hands. Now that they've met everybody, they can bounce as well. We continue in this fashion until all these people have had their turn being the special person. There's only 2 people left. Doesn't matter which one we choose to be the special person. They only have 1 hand to shake. They leave. Everyone shook everyone's hand. We're done. Thinking of the people as the vertices and the handshakes as the edges, we see that we come up with this exact same result that we had over here. The problem with doing the handshake problem this way is we still have to figure out what this sum is equal to. So we still need to either memorize this formula or have Gauss's method. What's kind of cool is there's a different way to do the handshake problem that makes it so you don't have to do that. So let's go back in time. We're in this little room. Everybody's drinking their drink, mingling awkwardly. No one shook anybody's hand. We got N people. This time we're going to do things a little bit differently. We're still going to start out by picking one special person, this purple person here, and we're going to have that person shake everybody's hand. That's N minus 1 handshakes. But then we're not going to tell that person to leave. What we're instead going to do is pick our second person and ask them to shake everybody's hand. That'll be a little bit awkward when they bump into the purple person because they will have already shook that person's hand, but they're under strict instructions to shake everybody's hand in the room. So even though they've already shook this person's hand, they're about to do it again. They're going to shake N minus 1 hands. Same thing for the third person. Even though they've already shook hands with 2 of the people in the room, they're just going to bite the bullet and shake those people's hands a second time as they walk around the room shaking everybody's hand. This person will shake N minus 1 hands, and so on. That'll be the case for every single person in this room. They'll shake N minus 1 hands. Some of them will be repeats, some of them won't, but we're not concerned with that. We're going to have a whole bunch of N minus 1s. How many N minus 1s are we going to have? Well, each of the N people in the room are going to be the special person at some point. So we're going to have N of these N minus 1s. But wait, you cry out. There's a problem. These aren't distinct handshakes. For example, purple and red shook hands when it was purple's turn, but then purple and red shook hands again when it was red's turn. In fact, that's true of any 2 people in this room. Every pair of people shook hands exactly 2 times. Once when it was the first person's turn, and then again when it was the second person's turn. By counting up handshakes this way, I've counted exactly twice as many handshakes as I should. So if I divide this product by 2, I figure out how many handshakes would be needed if every person shook everyone else's hand exactly 1 time. Note that this N times N minus 1 over 2 is exactly what we ended up deriving down here. Kind of cool, huh?